Good morning, sir.
Morning, Brendan. Okay, good morning, everyone. How are you today? Very chilly outside, very cold out today.
Good morning.
Good morning. Okay, well, welcome back, everyone, as we rub the sleep out of our eyes. We're going to get back into chapter 2 here. We have just a couple more definitions to talk about, and then we're going to start talking about chemical bonds, okay? So let me just remind you that, of course, next week, we are going to go back to school. We'll be together in the classroom. So, for your class next Tuesday, February 1st, please come to the Lancaster campus, 8 a.m. We will be in room East 227. Since this is our first time back on campus, I would encourage you to give yourself a little extra time. Sometimes there can be some parking issues and things the first day because there's a lot of chaos of people trying to get on campus. So give yourself a little extra time to make it to class and be safe, okay? Brendan, what can I do for you?
I got an email yesterday that's saying that it will reopen on the 5th.
Okay, so Brendan, I don't discount what you're saying, but I think there's been a bit of miscommunication from our administration. Here's what the deal is. Most of HAC's classes will start back on the 5th, but there are classes that are exceptions to that rule, and many of the science courses, including our course, we will be back in session next week. We will be back face-to-face next week. So please come to campus on the 2nd, okay?
Oh, thank you for clarifying, sir.
All right. Yes, I've read that email and I thought to myself, wow, that really wasn't communicated very well. So yeah, if there's any confusion, our 121 course will be face-to-face next Tuesday. Okay. All right, gang. Any other questions? Okay. Well, let's get started then. So at the end of last class, we were talking about a bunch of definitions to get the chemistry chapter started. We talked about atomic number, atomic mass, mass number, and isotopes. Okay, so if you do have questions about those, feel free to ask. Feel free to pop in during office hours and talk to me about things. That I encourage you to do that. Starting next week, I will have office hours physically on campus. So if you're on campus, stop by and say hello. All right, so I'm going to just continue with a couple definitions here, and then we'll start talking about chemical bonds. So some other terms, I am certainly not, you can tell, I am certainly not giving you a definition for every bold-faced term in the textbook. I mean, that would take forever to do, right? But so you do want to be studying your textbook. You want to be paying attention to bold-faced terms and things like that. I'm simply going to pick and choose the things that I want to highlight to you, okay? So the next thing is the term ion. If you've had any science background, you know that an ion is an atom, but it's an atom that has taken on an electrical charge, presumably because it has an abundance or deficiency in the number of electrons that are circling around the nucleus, okay? So an ion is an electrically charged atom. Okay, if you have a positively charged atom, such as sodium, that would be a cation. So cation is a positively charged atom. An example of that would be sodium ions that are part of table salt. And an anion is a negatively charged atom. An example of that, in fact, would be chloride, Cl minus. Okay, so we'll be talking about that in about 1 minute here. So we know that ions are electrically charged atoms. If you don't hear the phrase ion, then you should assume that the atom is basically neutral. Okay, now there are some nuances to that, and those of you that have had chemistry can appreciate that that's true. But as we get started, these are some ideas to think about. All right. Next is the term molecule. Okay, a molecule is a collection of atoms that are joined together by chemical bonds. A collection of atoms, at least two atoms, 2, 3, 4, maybe hundreds or thousands of atoms that are joined together by chemical bonds. Okay, so there's a related phrase that comes out, which is that of a compound. Okay, so let's talk about that a little bit underneath the topic of a molecule. So a compound is a molecule that's made of two or more different kinds of chemical elements, two or more different kinds of atoms. Okay, so for example here, water, right, H2O, water would be a very nice example of a compound. Okay, and something like atmospheric oxygen, the kind of oxygen that we're inhaling into our lungs right now as you sit in your room. Atmospheric oxygen is a diatomic molecule, meaning there's two atoms of oxygen. So O2 is not a compound. The reason it's not a compound is because both atoms in the molecule are in fact the same thing. Okay, so O2 is not a compound, okay, but it is a molecule. O2 is not a compound, but it is a molecule. Okay, and of course, water is a compound and it is also a molecule. Okay. Okay, question in the chat window. Are you okay with the difference between molecule and compound? You see that subtlety of the examples? Is that okay? Okay, thanks for the feedback. So please let me know if you do have questions. All right, the last thing I'll mention here in our definitions is that a topic known as a free radical. Okay. Now, when we talk about a free radical, we're not talking about political science here and extremist viewpoints about society. That's not what we're talking about. In the terms of chemistry, we're talking about an atom, or in some cases, a group of atoms that have electrons that are unpaired. And when you have electrons that are unpaired, where there's not a partner, those kinds of atoms seem to be very unstable. So in an attempt to be unstable, in an attempt to become more stable, those free radicals will go around and interact with other molecules and try to grab electrons from the other molecules. And when you do that, you damage the other molecule that's being interacted with, and that can have negative consequences for the health of your body, right? So if you have a lot of free radicals being produced in your body, those free radicals can actually go bouncing around like billiard balls on a pool table, and they can bump into molecules like DNA and damage the DNA, or protein and damage the protein. And then if the DNA or protein, of course, is not working properly because it was damaged when a free radical slammed into it, well, then that can have long-term consequences for our health, okay? So I have a question in the chat window. Are the lecture notes posted to D2L anywhere? No, Lauren, they are not posted to D2L. They are posted to Wiley Plus. That's where you should be going to get your lecture notes. Okay. So, okay, so a free radical is an atom or group of atoms that contains an unpaired electron. These atoms tend to be extremely reactive with neighboring molecules and often damage the neighboring molecule through that interaction. Okay, so if you ever hear anybody talking about that you want to eat particularly fruits and things that have a lot of antioxidants in, that's related to this idea of free radicals. Because if you have, if you're consuming food that has antioxidants in, basically you're saying you have molecules that can safely interact and kind of neutralize the free radicals. Okay, so that would be a good thing to have in your diet. Things like berries and various kinds of fruits are very good sources of antioxidants. Okay. All right, folks. So we've gotten the chapter started here with a number of ideas, a number of definitions, a number of concepts. So I'm going to take this and use this to transition into the first really major talking theme of the chapter, which is chemical bonds. All right. So, okay. First, what do we mean by a chemical bond? Okay, a chemical bond refers to a force of attraction that joins at least two atoms together. Okay, there are these invisible forces of attraction that can pull atoms towards each other. Those are the bonds. Okay, now the fact that they're invisible makes them hard to appreciate or think about. And while it's not quite the same thing, I would get you to think about the last time you took a magnet and you put it on your refrigerator. If you held the magnet and you got really close to the surface of the refrigerator, but you didn't let the magnet touch, you would have felt a little bit of tug, right? A little bit of drawing the magnet towards the surface of the refrigerator. That is kind of the invisible force we're talking about. Okay, now chemical bonds are not magnetism, but the idea of an invisible force is what I'm trying to get across to you in your mind, that there are these invisible forces that draw atoms towards each other. Okay, so chemical bonds are invisible forces that draw atoms toward each other. Okay. So there are actually a variety of different chemical bonds that science is aware of. There's three major ones that your textbook talks about, and so that's what we're going to talk about at this time. There actually are a bit more than three chemical bonds, but the three that are in your textbook is a very good start for an introductory course. Okay, so three major types of chemical bonds include ionic bonds, covalent bonds, and hydrogen bonds. Okay, and so the topic of chemical bonds begins in section 2.2 of your textbook, section 2.2, and as you read across your digital textbook, you're going to see major headings, are you not, of ionic bonds, covalent bonds, and hydrogen bonds. Okay, so please appreciate that no matter what kind of bond we're talking about, ionic, covalent, and hydrogen bond, we really are talking about a force of attraction between the atoms. Okay, so When I say number one up here, chemical bonds are invisible forces that draw atoms towards each other. That is true for all three types of chemical bonds. Okay. So sometimes when students start reading the textbook, they start reading it and they say, okay, well, there are ionic bonds. I'm reading that. I get it. And there's covalent bonds. I'm reading that and I get it. And there's hydrogen bonds and I'm reading that and I get it. And so you think there's three different types of bonds, but the bonds have to be different because they're given different names. Ionic bond must be different than a covalent bond, must be different than a hydrogen bond. And while there are some subtle differences between these bonds, I would kind of like you to think about it oppositely. I would like you to think about ionic, covalent, and hydrogen bonds as basically three sides of the same triangle. Okay, think about these bonds as three sides of the same triangle. Yes, it's a different side, but it's still part of the same triangle. Okay, so there are differences, but there's also a lot of similarity here. Okay, so let me go back up here and state that all three bonds are really different sides of the same triangle. Different sides of the same triangle. Okay. So let's start talking about each one. Okay. So let's consider the ionic bond first. There's no reason I have to talk about that first, but it is listed first in your textbook. So let's do that first. Okay. So number 3 here, consider ionic bonds. Okay, so let's define an ionic bond, and then we can try to talk about it by doing a little bit of drawing. Okay, so an ionic bond is an attraction created when one or more atoms donates one or more electrons to a neighboring atom, period. Okay, an ionic bond is a force of attraction created between atoms when one atom donates, or you might say transfers, one or more electrons to a neighboring atom. Okay. And again, of course, that force of attraction is invisible, but we can measure these things in the research lab. We know that they exist. There's an abundance of evidence that shows that these things are real, even if we can't see them with our eyes. So, excuse me. All right. So let's talk about a traditional example of a substance that would have ionic bonds in it. Okay. And the example comes right out of your textbook, figure 2.4. And it's the topic of sodium chloride, abbreviated NaCl, which is the same thing as table salt that you have on your kitchen counter. Okay, so all right, so I'm going to try to do a little bit of drawing here on our digital document. Hopefully it will go well. Sometimes it doesn't. So let's see how it goes today. All right. So for a moment, just bear with me here. Okay. So, all right, let's say that I have two atoms, sodium and chlorine. Okay. And notice that I put some intentional space between these two atoms. I have a sodium atom drawn on the left with a little bit of white space, and then a chlorine atom drawn on the right side. And that space is intentional right now because I'm trying to suggest to you at this moment that sodium and chlorine are in fact not interacting. They're not interacting because right now in our conversation, there's no force of attraction. So there's no force of attraction because right now, according to chemical theory, all the atoms on the periodic table of elements should be considered electrically neutral. Electrically neutral. Okay. So that's where chemical theory starts. And you will get a much more sophisticated version of that in a full-fledged undergraduate chemistry course. But chemical theory, ideas that mankind, human beings, have created over the years, starts on the premise that the elements of the periodic table, as we think about them, should be thought of as objects which are electrically neutral. It is disturbances in that foundational idea, in other words, when things do not remain neutral, that attraction or repulsion can exist between atoms. Okay, so let's take a look here, and I want to show you that you are all capable of reasoning your way to some logical conclusions about this. Okay, so I'm going to ask you to have your digital textbook open and please turn to figure 2.2. Please turn to figure 2.2. Okay, and so I'm just going to kind of go around the room a little bit here. And let me take a look at my participant list here. Okay, Naomi Myers. Naomi, can you say hi to us?
Hi.
Hi, Naomi. Naomi, do you have your digital textbook open in front of you?
I do.
Okay, great. So Naomi, I want you to look at figure 2.2 in your textbook, please. And so Naomi, I'm going to ask you a couple questions about the information in figure 2.2 and ask everybody in the class to follow along. So Naomi, my first question to you is this. Looking at the information in figure 2.2, how many protons are in the nucleus of a sodium atom?
Would that be 11?
It would be 11. Nicely done, right? Because we know from last time that the phrase atomic number refers to the number of protons. Nicely done. Stay with me, Naomi. You're doing just fine. So Naomi, on the screen, I'm going to write down next to the sodium atom, I'm going to put the number 11 with a positive or plus symbol indicating protons, okay? So Naomi, if this sodium atom has 11 positively charged protons, then Naomi, how many electrons must it have to be a neutral atom?
Would it have to be even then?
Yes, I think you have the right idea. So could you tell me how many electrons need to be present?
So it'd be 12?
No, it wouldn't be 12 because if I had 11 protons and 12 electrons, I'd have an imbalance. So
Oh,
you
so
want to
it'd be
go ahead.
22.
Okay, so how many electrons should be present? So Naomi, think of yourself being at the playground on a seesaw, and I know you can't see my arms because my camera is cutting them off. But imagine that neutrality represents a balanced seesaw, and if I have 11 protons on one side, how many electrons do I need on the other side to make the seesaw level?
11.
Good, there you go. You need 11.
Oh, okay.
That's what I mean by being electrically neutral, is that we have a level balanced seesaw. So if I have 11 positive things on one side of the seesaw, I need 11 negative things on the other side of the seesaw. Okay, good job, Naomi. Stay with me here. So I'm going to put down 11 electrons here. Okay. So Naomi, continuing this conversation, Naomi, how many protons does a chlorine atom have?
17.
Okay, good job. So tell me, if that's going to be a neutral atom, how many electrons does it have?
17.
You got it. Nicely done. Okay. There we have two atoms that are electrically neutral. Thanks, Naomi. I appreciate your participation today. Okay. Okay, Alana Sterner. Alana, can you say hi to me?
Hi.
Hi, Alana. Alana, are you able to take a look at figure 2.2 at home?
Yeah.
Okay, great. And so, Alana, you okay so far with our conversation of what an electrically neutral atom means?
Yeah.
Okay, all right, so good. So what we need to do now is talk to you about, well, okay, if these atoms stay electrically neutral their entire lifetime, there is not going to be an attractive force created, and the sodium and chlorine will stay apart from each other. There's no reason for them to interact because there is no attractive force. The attractive force takes place when there is actually a removal of the neutrality condition on each atom. When each atom is no longer neutral, then we create the circumstances needed for attraction, or in some cases repulsion, to take place. Okay, so Alana, let me ask you this, and let's just walk through this logically here. Okay, Alana, let's say, for reasons that we're not completely defining at this moment, let's say that sodium, for some odd reason, decides to get rid of one of its electrons and eject it over to chlorine. So I'm going to have one electron from sodium going over to chlorine. So if that happens, Alana, if sodium ejects one electron, how many electrons are going to be left around sodium?
10.
10. Okay, so I've got 10 electrons around sodium after it gets rid of one. So now, Alana, if I have a sodium atom that now has 11 protons and 10 electrons, what's the overall state of balance or imbalance going to be here? What's the overall charge on this sodium atom going to become?
It's like a positive charge
Why?
because is it the like cation or something? Because it has more protons than electrons.
Okay, I like your answer there. It now has more protons than electrons. Alana, how many more protons than electrons does sodium have in this circumstance?
Just one.
Just one. So the overall charge on the sodium becomes a +1, right? So this now becomes the overall charge because sodium ejected an electron. Okay, good job, Alana. Stay with me here. So continuing with our line of reasoning, if chlorine accepts the electron from sodium, then how many electrons would chlorine have, Alana?
18.
It would have 18. And so now, Alana, with this new circumstance, what would be the overall charge on chlorine?
It would be like -1.
Good job. Fantastic. Thanks for participating today. I really appreciate it. Okay. All right, folks. So now we have overall charges on each respective atom as +1 for sodium and -1 for chlorine. And if you recall anything from any moment of your life where you've heard the phrase opposites attract, that is true in this circumstance as well. We have a sodium with a +1 charge and a chlorine with a -1 charge. So that will create a force of attraction, that invisible force of attraction, which is the chemical bond. And these atoms will be drawn towards each other, so that we'll now have sodium and chlorine like this. Okay, so here's the invisible force of attraction. This is the invisible bond, if you will, that's created. Okay. So any questions at the moment? Okay, so if you're okay with what just transpired on the screen, you know, I'm hoping as your teacher, I'm hoping that there are a couple questions in your mind, such as, well, okay, I get the logic of just what you showed me, but why in the world would sodium get rid of an electron? Why would it do that? And why in the world would chlorine accept an electron? Why would it do that? After all, sodium and chlorine were electrically neutral when we started. Why should they change their neutrality? Why should that situation change? Well, it has to do with atomic structure. And while I'm not a chemist and I won't pretend to explain all the nitty-gritty details of that to you, if you look at figure 2.4, you can see in figure 2.4 that, all right, you can see in panel A that the sodium atom actually gets rid of an electron. Do you see the phrase in picture A, sodium, 1 valence electron, 1 valence electron, okay? So the reason that sodium ejects an electron is because it only has 1 electron in its 3rd electron shell, okay? As you look at the sodium atom, you see the green circle, which is the nucleus, and you see 3 green rings around the sodium nucleus. Each ring represents a ring of electrons. And generally speaking, electrons like to pair up and buddy up in groups of 2. And if you only have 1, well, then that ring is kind of unstable and the atom is unhappy about it. And so to become more stable in its atomic structure, sodium has the tendency to get rid of an electron. By getting rid of an electron, it does not have an unfilled outer electron shell. That's what chemical theory attempts to use to explain why sodium gets rid of an electron. Okay, so let's just write some of this down in some basic notes here. Okay. Why does sodium eject an electron? Okay, it ejects an electron because its 3rd outermost electron shell is unfilled, and that creates an unstable condition for the atom. The 3rd electron shell is unfilled, which means the atom is somewhat unstable. And so in an attempt to become stable, you could either eject 1 electron and get rid of that 3rd electron ring altogether, or you could find additional sources of electrons to fill up that 3rd shell, which in this case, you'd need 7 additional electrons. So let me ask you this in the chat window. Hold on a second. Here we go. If you could accomplish a goal in 2 different ways, number 1, by getting rid of 1 object, or 2, by acquiring 7 objects, which option is probably easier to do, right? If you could make yourself happy by getting rid of something you already have, or trying to acquire 7 things you don't have, well, what's going to be the easier situation? get rid of the one you do have, right? That's going to be easier. So from that perspective, Mother Nature seems to be pretty pragmatic. So the sodium ejects the electron to get rid of that outer electron shell so that the sodium atom can be more stable from an atomic perspective, okay? If you want a deeper understanding of that, you will need a proper chemistry course. And you know, in chemistry, they're going to talk to you about different kinds of electron shells. And if you get really mature in your chemical understanding, you're going to be introduced to things known as quantum mechanics. Quantum mechanics, honestly, is not for everyone. It's a hard topic to talk about. It's a hard topic to understand, and it requires a pretty sophisticated level of understanding of calculus in order to do the understanding. Okay, so we're not going to touch that. We don't need to touch that at our level of instruction here. So why does sodium eject an electron? To make itself more stable by destroying or removing its third outer shell. That makes the atom more happy. And so you might ask the equivalent electron, you might ask the equivalent question, why does chlorine accept the electron? Because if you look at the chlorine description on figure 2.4, don't you see that its third electron shell is almost complete? It's got 7 electrons. It only needs one more. It only needs one more. So it seems like a match made in heaven that sodium can make itself happy by getting rid of 1 electron. Chlorine can make itself happy by accepting 1 electron. Hey, that's a perfect relationship there from an atomic perspective. Okay. So why does chlorine accept an electron? And the answer is, by accepting 1 electron, it can complete its third outer electron shell, which makes the atom more stable, more in very rough language, happy. Okay. One additional electron is needed to stabilize the third ring of electrons. And again, if you're thinking about this, you know, when you're thinking about the notes, you know, in 2 weeks from now, and you're going back to review, remember, this is all in relationship to figure 2.4 here that we're having this conversation. Okay, gang. Would you like to ask any questions about this topic? Okay. If you're okay, let's keep rolling here. And so let's see, the next topic is going to be that of covalent bonds. Okay, so letter B, covalent bonds. Okay, so covalent bonds, let's start out with the definition. A covalent bond is an attraction created between atoms when the atoms share the electrons. It's not that one atom gives an electron away. It's not that one atom completely accepts that electron. It's that when the atoms are sharing electrons, and the shared electrons spend some percentage of their available time orbiting the nucleus of both atoms that are participating in the bond. Okay. This is a force of attraction created when one or more atoms share one or more electrons. Okay. So the key phrase in the definition for ionic bond would be donates. That would be the key phrase for the ionic bond. The key phrase in a covalent bond is share. In the covalent bond, the atoms are sharing their electrons, okay? And so there's a number of things to talk about here. Covalent bonds are highlighted in figure 2.5, so that's a useful figure to start thinking about these things, okay? And so let's see here. Let me give you some examples here. And I'll start by saying that there are two categories of covalent bonds that we should really consider to properly understand biology. Okay, there are two broad categories, or perhaps you prefer the word types, of covalent bonds. And those types would be nonpolar covalent bonds and polar covalent bonds. So what I want to do at this time is give you examples of each. Okay, so let's do that. So the first thing, I'll give you an example of a nonpolar covalent bond. In terms of figure 2.5, some very nice examples of nonpolar covalent bonds would be the first three pictures you see in figure 2.5, where you see panel A, panel B, panel C, and you get two atoms of hydrogen together, that would be nonpolar. When you have two atoms of oxygen together, that would be nonpolar. When you have two atoms of nitrogen together, that would be nonpolar. Okay, and I'm going to use an even different example here, but in figure 2.5, you can consider H2, O2, and N2 to be examples of molecules where the atoms are connected by nonpolar covalent bonds. And the example I'm going to use with you is actually carbon at this time. So carbon bonds are also nonpolar covalent bonds. So let me give you an example here by kind of drawing this out in a cartoon fashion. So what we have here, and let me do this. So I'll draw some purple colored things here. So here's a nonpolar situation. Okay, so if you have a carbon bond, this is going to be nonpolar. Well, first off, what does that even mean? Well, that means that there is an equal sharing of electrons. This little dashed line here, between the atoms is sort of a symbolic representation of the electrons being shared. Okay, so that line is a bond, and it's trying to tell you that we have some shared electrons at this point. Okay, and so remember that the best that I can do is put something on the screen or on the whiteboard for you, and the best that your textbook can do is show you a picture of something, but it's a very pale shadow, a very pale representation of reality, because the electrons that truly exist between the atoms, carbon on one side and carbon on the other side, those electrons, obviously we can't see them with our naked eye, but they're there and they're in constant motion. Heat energy in the environment ensures that they're constantly moving. So the electrons are in constant motion, and they never stop for the most part. Okay, they never stop. And so if I were to redraw this slightly differently, I would redraw it like this, where I have a carbon atom here and a carbon atom here. And then I would take a different color, and I'll just make it, let's make it green, I guess. Oh, let's make it red just so it really stands out, okay? And so what I'm going to draw is a dashed line representing the continual motion of the electrons being shared. So the electrons would kind of look like this. I'm not much of an artist, but what I'm trying to get you to see is that the electrons are going around like this in this pattern. They're basically forming a figure 8 where they spend roughly 50% of their time moving around the nucleus of the left carbon atom, and another 50% of their time orbiting the nucleus of the right carbon atom. In other words, you know, if we could somehow stand back and look at the visual impression of the cloud of image that the electron motion creates as it's moving around, we would kind of start to see different geometric patterns, like figure 8s or circles or ellipses or other exotic kinds of geometry where there's a volume of space that those electrons are occupying around each atom roughly 50% of the time. Okay, so the electron in a nonpolar situation, we have an equal sharing of electrons. Now, please be clear on this. When I say you're sharing an electron, I'm not talking about the electron being equivalent to a pizza, and you cut up the pizza into 8 equal segments and you give 4 to your brother and 4 for yourself. That's not what's happening here. We're not dividing up the electron. We're not cutting it in half in any way. But what we are doing is dividing the time of the electron. 50% of the electron's time is spent around one atom. The other 50% is spent around the other atom. So we have an equal sharing of time. Equal sharing of electron time. Okay. Folks, are you okay right now? Any questions that you might want to ask? Okay, let's keep going here. I appreciate that sometimes you're looking at this stuff and you're like, well, I'm sure I don't understand it, but I don't even really know what to ask. I mean, that comes up, right? So I want you to, as you start really thinking about this and studying this, if you do have questions, write them down. Write them down, shoot me an email, bring them into the classroom. Let's talk about them, okay? So to complete this topic, let me change gears here a little bit and talk about the polar covalent bond circumstance. Polar covalent bond, let me have a dividing line here. Polar covalent bond would be something like this. Okay, well, let me see. I don't want to, hold on a sec. I want to make your notes a little bit cleaner. And so I'm going to hopefully go down to the next page. Okay, so we now have an example here of nonpolar bonds. Okay, and you can take a look at those. Now let's go down here and do another example from figure 2.5 of polar covalent bonds. Okay, and for this one, you could use the CH4, so that would be panel D as in David of figure 2.5. The molecule CH4 is going to have polar covalent bonds in it. and also water. Water is going to have polar covalent bonds in it as well, H2O, okay? And so I will use water as a talking point here to illustrate this for you, okay? So let's do the example of polar covalent bonds here. Okay, now I'm gonna, what I'm gonna talk about, I'm gonna start talking about oxygen-hydrogen bonds, which obviously are part of the structure of water, right? H2O. H2O has hydrogen, has oxygen. So you should expect that there are polar covalent bonds in water. So if we have oxygen with a polar covalent bond in hydrogen, well, that would be the first way of representing it. And again, if I draw it differently to try to represent the motion of electrons, I would draw it kind of like this. All right, and here we go. Okay, and so the first thing I want you to appreciate is, even though I'm not much of an artist, when I drew that figure 8 around the nonpolar carbon-carbon atoms, I tried to make the size of the lobes of the figure 8 roughly equivalent in dimension, roughly equivalent in space, roughly equivalent in volume. But you see that the lobes around oxygen and hydrogen are nowhere close to being equivalent. The volume of space occupied by electron motion around the oxygen is significantly greater than the volume of space around the hydrogen atom. And so the thing that characterizes a polar covalent bond is an unequal sharing of electrons. An unequal sharing of electrons. Okay. And so just as a rough approximation with the example of oxygen and hydrogen, maybe you see that the electrons spend 80% of their time around the oxygen atom, and maybe they spend 20% of their time around the hydrogen atom. So that would be an unequal sharing of the electrons' time. Okay. And so, you're going to find both categories of bonds in different types of molecules. But one key feature that you might want to think about is that at least the examples we gave you for nonpolar bonds, the nonpolar bonds typically form when you have two atoms that are exactly the same type of atom on both sides of the bond, right? So a carbon-carbon bond has a carbon atom on the left and a carbon atom on the right. A nitrogen-nitrogen bond has a nitrogen atom on the left, a nitrogen atom on the right. So if you see a bond between two atoms where the atoms are the same type of atom, then that's going to tell you, with some exceptions we won't go into, that pretty much that's going to be a nonpolar bond. So think of the line drawn between the atoms as sort of a tug of war rope, and we have two teams where we're doing a tug of war, and two teams are exactly identical. It's kind of like you having a tug of war against a clone of yourself. So if you had a tug of war against yourself, you would both be able to pull on the rope in opposite directions with the same amount of force. So basically, the dangling flag on the rope is really not going to spend any more time on one side versus the other. It's going to be roughly equal, okay? But if we go down to the tug of war analogy here for a polar covalent bond, that would be like you having a tug of war with Arnold Schwarzenegger, right? At least a young Arnold Schwarzenegger when he was really, bodybuilding. So in that scenario, probably Arnold would win most of those tug of wars, right? So he would pull the rope predominantly towards his side, occasionally you might jerk it back to your side for a little bit of the time, okay? So notice here with polar covalent bonds, these usually can be predicted by the fact that the two atoms on opposite sides of the bond are different. Predicted by two different atoms participating in the bond. Whereas the nonpolar scenario can be predicted by having two identical atoms participating in the bond. Okay, now I want to show you one more thing here. Okay, one more thing here about these bonds, and again, show you that you can start to reason your way to a lot of good thinking, simply by looking at some information that you have available in your textbook and thinking about ideas we've already covered. Okay, so let's go here. Okay, let's see. Let me try Jared. Jared, could you say hi to us?
Hello,
Hi, Jared. How you doing today?
I am well. How are you?
Okay, a little cold this morning, but I'm okay. So Jared, do you have access to figure 2.2 in your textbook?
Yes.
Okay, so everybody please follow along in figure 2.2 and listen to the conversation I'm having with Jared. So Jared, what I want to do is have you interpret information in figure 2.2 and show you that you can actually predict why the electrons in the oxygen-hydrogen bond spend more of their time around oxygen than hydrogen. Okay, that's our goal here. So Jared, when you look at the information in figure 2.2, Jared, can you tell me how many protons an oxygen atom has?
8 protons.
Okay, good. And how many protons does a hydrogen atom have?
Just 1.
Okay, so Jared, does it make logical sense to you that if we're thinking about a tug of war analogy, if I have 8 team members on one side, 8 protons, which are going to attract electrons toward themselves, and on the other side of the tug of war rope, I have a team with 1 team member, hydrogen, that has 1 proton, that team hydrogen is really outmatched in terms of pulling electrons towards itself.
Right. Because there's more of a positive charge with the oxygen, attracting the negative charge more than the hydrogen.
Beautifully restated, Jared. Thank you for your participation today. That's exactly what I wanted. Good. Okay. All right, gang. So just notice here, notice in figure 2.2 of your textbook that oxygen atoms have 8 protons, while hydrogen atoms have 1 proton, which explains why oxygen is a more powerful electron vacuum cleaner, can draw electrons towards itself better because it's got 8 teammates which happen to be positive protons. Sorry for my sloppy writing here. I'll read this to you. So notice in figure 2.2 that oxygen atoms have 8 protons while hydrogen atoms have 1 proton. Oh my goodness. You can tell I'm a biologist because I wrote down protein, didn't I? Okay. So let me just correct this for you here. Okay. While hydrogen atoms have 1 proton, which explains why oxygen is better at attracting electrons, okay? There's another idea that I'm not going to talk about, but I would like you to think about during your private study time, and I'm going to highlight it here right now in green. So I want you to at least study a little bit about electronegativity. A little bit about electronegativity, which is a term that does come up in your reading. I'm looking at it underneath the text of covalent bonds in your textbook. For me, that's page 35. There is that term electronegativity. And so be sure that you're at least thinking about this a little bit during your private study time. Okay. All right. So folks, we've covered two of the major bond types. We've covered ionic bonds and gave you an example of sodium chlorine. We've given you an example of several different covalent bonds. We described nonpolar covalent bonds. We described polar covalent bonds. Okay. Questions at this time? Okay. Everybody's quiet, so I hope you're not passed out at home. Let's continue here. So the next talking point and sometimes, come on, I'm trying to get my technology to work here. Okay. Sometimes it's suspenseful because I'll do things and the computer will just blow up on itself. Okay. So our third type of bond to cover is hydrogen bonds. Okay, so that would be letter C in our notes. Let's talk about hydrogen bonds. Okay, so let's define what hydrogen bonds are. A hydrogen bond is an attraction created between a slightly positively charged hydrogen atom and a slightly negatively charged atom, typically oxygen, nearby. Okay, so this is an attraction created between a slightly positively charged hydrogen atom and a slightly negatively charged atom, often oxygen, nearby. Okay, so this is a topic that is covered the textbook section, hydrogen bonds, under section 2.2. You see figure 2.6 in your textbook, which helps understand what this stuff is. Okay, so let's talk about this a little bit with the remaining time we have available. And so I'm going to talk to you about hydrogen bonds in the broader context of water. And I will reference figure 2.2, figure 2.6 in your textbook here. And so let's do a little bit of drawing. Okay. So let's say that I put a water molecule here in your notes. Okay. So I'm going to draw H2O. Okay. So let's see here. Ray Ober. Ray, could you say hi to us?
Hello.
Hi, Ray. How are you today?
Good.
Okay, Ray, please speak nice and loud for us so everybody can hear you. So Ray, on the screen, I have a water molecule that I drew with some purple colored letters here. And I'm going to put a green box around these bonds. Ray, could you tell me what kind of bonds these are that I'm putting in the green box?
Non-polar.
They are not nonpolar. Do you want to try again?
Polar.
Polar what?
I'm not sure.
Okay, so Ray, follow me on my computer screen, okay? We said up here that there's two broad categories of what bonds?
Covalent.
Okay, so what kind of bonds are these that I'm highlighting?
Covalent then.
Okay, and specifically what type of covalent bond?
Polar.
So these are polar covalent bonds. Okay, good, Ray. Stay with me. Okay, so these are polar covalent bonds. All right, so you appreciate, and everybody appreciates, that typically when we're talking about water, unless it's a chemistry course, we're not really talking in everyday life about one water molecule. I mean, if we only had one water molecule, what hope would we have? What hope would we have of filling up our swimming pools, right? So let's do this. Let's add another water molecule to this drawing. Okay. So Ray, I'm going to highlight these bonds in orange. Ray, come on here. Computer, work with me, would you please? Okay, hold on a sec. Try again. Okay, so Ray, what kind of bonds are these bonds?
Is it still polar?
Give me the
Covalent?
whole, yeah, yep, always give me the whole thing. They are polar covalent, good job. So these are polar covalent. And the first thing, perhaps obvious or not obvious, that I want to point out is that within the context of each individual water molecule, right, as I move my cursor around the top water molecule, or as I move the cursor around the bottom water molecule, the point is that the bonds between atoms inside each water molecule are polar covalent. We don't get the hydrogen bonds forming between atoms within the same molecule. We get the hydrogen bonds forming between atoms that are part of two different water molecules. Okay. And so I'm going to just draw this as a dashed line, red right here. This is the hydrogen bond. Okay. All right. Okay, thanks, Ray, for your participation today. I really appreciate that. Okay, so we're getting a little close on our time, and I don't want to get too much into the weeds, but certainly the question becomes, why does this hydrogen bond form? Why is there a source of attraction between the top hot oxygen atom of the top water molecule and the hydrogen on the bottom water molecule? Why does this force of attraction exist? What creates it? And what I'm trying to show you here is that this attraction forms because before it forms, the bonds within each water molecule are polar covalent. Okay, so what that means is that, let's see, I'm running out of good colors here to use, but I'll use black. I'll use black. Okay, so think about the top water molecule. The top water molecule, And let's think about this first hydrogen-oxygen bond right here. Okay, the first hydrogen-oxygen bond. It's polar, right? So there's an unequal sharing of electrons. That means most of the electrons in this bond, and maybe I should just dash it out for you here. Okay, so this is the bond we're currently looking at. Okay, the bond that's been outlined in a dashed yellow rectangle. That's the bond I'm talking about. The electrons that are being shared between that hydrogen and that oxygen, well, they spend most of their time around oxygen. Why? Because oxygen has more protons. We showed you that 5 minutes ago when we were having this conversation. So that means that this oxygen takes on a partial positive charge. Okay, so this is a symbol which means partial positive. This would be a symbol which means partial negative. Okay, so the oxygen on the top molecule takes on a partial positive. Excuse me, I'm sorry, I just drew that wrong. Sorry, folks. It takes on a partial negative because it's drawing electrons towards itself. Sorry, I didn't mean to confuse. The hydrogen takes on a partial positive because it's losing its electron a majority of the time, because its electron is being drawn towards the oxygen. So oxygen takes on a partial negative, hydrogen takes on a partial positive. That situation is going to exist around every water molecule. So this oxygen becomes partially negative. This hydrogen takes on a partial positive characteristic. Do you see that I now have the oxygen of the top molecule with a partial negative charge and the hydrogen of the bottom water molecule having a partial positive charge? And if that situation unfolds, then you are in fact going to generate a source of attraction between those two atoms. And let's see, I'm really kind of running out of good options for coloring, but now what I'm talking about is this source of attraction here. The partially negative oxygen and the partially positive hydrogen, both which are atoms of two separate water molecules, are now attracted to each other. Okay. So let me ask you this in the chat window. So hold on a sec. Here we go. Everybody please read and answer. Go ahead. True or false? If the hydrogen-oxygen bonds within each water molecule were actually nonpolar, the hydrogen bond would not form. Okay, so thanks everybody that's participating. And I'm seeing a consistency in your responses, which is encouraging, because that means you're either consistently right or you're consistently wrong as a group, right? So, and the answer to that question is definitely true. Definitely true. So good job, everybody. And that's, the only way I know if you're understanding is if you answer questions correctly. That's why we have exams. That's why we have tests, right? So if this were on a test posed like this, you would have all got this question correct. So nicely done. This is absolutely true, right? The only reason the hydrogen bond forms is because the individual oxygens and hydrogens take on slight charges. In the case of oxygen, a slight negative charge. In the case of hydrogen, a slight positive charge. The only reason you get these slight charges is because those atoms themselves within each respective water molecule are participating in polar, unequally balanced sharing of electrons with another atom within that same molecule. So if those particular bonds within each molecule were in fact evenly sharing electrons, these partial charges on oxygen and hydrogen would disappear, and then there would be no foundation for the attraction anymore. Okay, so this is the reason that hydrogen bonds form, because the molecules in the environment themselves possess polar covalent bonds. And whether it's apparent to you at this moment or not, and this is something that takes some time, this ability to build hydrogen bonds explains a lot of other features of reality that we experience, such as, why you can change the melting temperature of water when you put salt on the road. Think about it, right? We're in winter time. We deal with snow and rain and freezing rain, and it's a miserable, rotten time to be driving a car. Well, so if bad weather is predicted, what do the municipalities do? They go along, they throw some salt down. When they throw salt down, that's able to keep the precipitation in liquid form longer by disrupting the water's ability to form hydrogen bonds. Because if you can form the hydrogen bonds, the liquid water transitions to ice more quickly. And that's exactly what we don't want when we're driving. Okay. All right, so I'm over time as usual, so I'm going to stop. Okay, I'm going to stop.